All right, chemistry students, let's look at the Chapter 10 review questions at the end of this chapter, Chapter 10. And of course, the answers I provide you, but we'll go over these and we can just talk about them a little bit. Maybe that'll help you just comprehend these ideas a little bit better. Number one says, what idea is the kinetic molecular theory based on? Basically, you must understand that particles are always in motion. That is the idea, the basis, the main concept for the KMT, kinetic molecular theory. Particles are always in motion, even solids. Those particles are just vibrating, kind of in place in a fixed location. Number two, state the 5 basic assumptions of the KMT. So you should be able to identify them or maybe state them in your own words. Of course, let me just walk through the different statements. And again, yes, they're written here for you, but you should be able to understand what they're saying and maybe just kind of tailor these statements to your own vocabulary. So one, gases consist of a large number of tiny particles that are far apart. Remember, a gas in a container, that is mostly empty space. Okay? Number two, the particles in a gas are in constant rapid motion. All collisions between gas particles and other gas particles or the container walls are elastic. Remember, they bounce off each other and they keep going. No loss of kinetic energy. Number four, there are no forces of attraction between gas particles. They don't get close to each other and then kind of hang out, shake hands for a little while, and then move on. They just pass each other, don't even notice each other, keep moving on, or bounce off each other and have no loss of total kinetic energy. And then the average kinetic energy of the gas particle determines the temperature. The temperature is measuring the average, not the individual of every particle. Those can vary, but the average overall kinetic energy. And remember that kinetic energy is measured by taking 1/2 times the mass times the velocity squared. So lighter particles at the same temperature as heavier particles will be traveling faster. Lighter particles at the same temperature as heavier particles have to travel faster in order to get the same kinetic energy as the heavier particles. Okay? All right, let's go back to the questions here. Those are the 5 assumptions. We just talked about those right there. How do gases compare with liquids and solids in terms of the distance between their molecules? So gases, you should know the particles are much farther apart for gases than they are for liquids and solids. Gases are much less dense. Solids and liquids are more dense. Number 4, what is the relationship among the temperature, speed, and kinetic energy of gas molecules? All right, so you have temperature. Temperature is not the same as kinetic energy, but they are related. It's measuring the average. It's a measurement of the average kinetic energy. Kinetic energy is 1/2. There's actual calculation we can do here, 1/2 mv squared. Okay, so here's the deal. If the average, usually we put a line over something to show that it's average, the average kinetic energy, as that goes up, so does temperature. It's a direct relationship. Now we have different scales for temperature. We have the Kelvin scale, the Fahrenheit scale, the Celsius scale, but all of those measurements, the temperature will go up as the kinetic energy goes up. Now, understand, in your kinetic energy formula, there is mass and there is velocity. Okay? So if you have a particular particle, if that particle's mass is not going to change over time, but if its velocity increases, because you're going to add energy to it, if its velocity increases, it has more kinetic energy, and therefore the temperature of that substance will go up. Okay? Also remember that if you're comparing two particles, and they're at the same temperature, let's say you have a mix of different gas particles in the same container, all of those particles in the same container have the same average kinetic energy. The heavier particles are going to move slower. They can have the same kinetic energy as lighter particles that are moving faster. The lighter particles must move faster to have the same kinetic energy as heavier particles that are moving slower. Okay? All right. What factors affect the rate of diffusion of one gas to another? Now remember, diffusion is the mixing. All right? One gas through another. Well, if those particles are moving slowly, think about, like, people at a party and they're mixing. Well, those people are going to mix and meet different people at a slower rate, diffusion rate, if they are moving more slowly. If they're moving really quickly, you can go around and rapidly meet a whole bunch of people and the whole room gets mixed up and it's very random. Okay? So what are some factors that affect the rate of diffusion? One of them is going to be the temperature. The higher the temperature, the faster particles moving, the more they're going to be spreading around. Okay? Let's see some other ones here, if there's any others. Oh, that's it. We basically have that. Factors affecting the speed of each type of the gas particle. And that speed, as I go back here, the speed of those particles, influence the kinetic energy, which is measured, the average kinetic energy is the measurement of temperature. Okay? So basically it is going to be the speed of the particles. The faster they're moving, the faster they're going to diffuse. All right, surface tension. Surface tension is when you have basically a liquid, and that liquid on the surface, because these surface particles here are attracted to each other and attracted to the particles below them, are going to form kind of a barrier here, a nice, almost like a platform that you can put a little bit of force on there and not break through, because there's attraction between all these particles, and that creates surface tension. Okay? List at least 3 properties of solids and explain each in terms of the kinetic molecular theory. Okay, let's refer to the answer sheet for this, and we'll go through them. Again, you could have lots of different answers here, but solids, you must know that they have a definite shape. They don't just fill whatever container they're in, and that's because they have a fixed, definite placement of their particles. They have a fixed arrangement. Okay, again, we're explaining this in terms of what's happening at the molecular level. Solids have a definite volume, and again, that's because they're packed closely together. They don't just expand and keep moving outward and just take up and fill the whole container. They have definite melting points. All right, you have to reach a certain temperature in order to start to break those intermolecular bonds that are holding them together. You have to reach temperature, and that specific temperature, depends on how strong the bonds are between the different particles. Okay? And they have high surface densities because of the close packing. So they're packed close together. You cannot, using pressure, you can't really compress them anymore, so they're incompressible. And they have low diffusion rates because the particles don't move very much. They're fixed in place. So you should be aware of all of those. Okay? All right, next question here is, list and describe 4 types of crystals in terms of the nature of the component. Okay, I am not going to ask you to be aware of the different types of crystals. Okay, don't have to worry about that. All right, using the graph, energy distribution of molecules in liquid at different temperatures, estimate the equilibrium vapor pressure of each of the following at a specific temperature. Okay, all you have to do is just read a graph, refer to a graph. So we're going to go up to this graph, energy distribution of molecules in a liquid at different temperature. Let me just look at the title again. Energy distribution of molecules. In other words, how much energy are the molecules going to have in a liquid when they're at different temperatures? Okay? And we're going to look at water at 80 degrees Celsius and ethanol at 60. And what are we looking for? The equilibrium vapor pressure of each of these here. So we got to go way back up here to that diagram. I don't think I talked about it if at all, but we can still read from this. Here it is. All right. All right, so here we have number of molecules. As the number of molecules is going up here, and here we have kinetic energy increasing this way. Okay? All right, so basically we're looking at this and seeing, realizing that the energy distribution of molecules in a liquid at different temperatures. So as the temperature increases, what does that mean? You're going to have more or less molecules. Okay, here's the deal. So this is lower temperature, higher temperature. Okay, so this curve right here is showing a lower temperature. They don't give you the specific temperature. Here you have a higher temperature. Okay, so what does that mean? As the kinetic energy increases, here, that means, remember, Ke equals 1/2 mv squared. At low temperatures, you're going to have lots of molecules. Here's the peak. Lots of molecules that have lower kinetic energy, okay, at lower temperature. Makes sense? Lower temperature and kinetic energy are connected. At higher temperature, this curve is shifting toward higher kinetic energy. Higher temperature, you're going to have more particles. The maximum here is at a higher kinetic energy. Okay? It says a larger portion of the molecules in the warmer liquid have enough kinetic energy to enter the gas phase. So as this curve shifts in that direction, more and more, see this portion right here? This is the line right here where they have to have this much kinetic energy in order to go from the liquid to the gas. All right? This curve here is showing you that there are a few here that have that energy in order to vaporize. But here, if the temperature is higher, you have even more. Now look at the area under this curve. You have a lot more particles that have enough energy to go from liquid to gas. Okay? All right. There might be another curve that we refer to here because they want specific values. Here we go. This one. I think they're referring to this one here. All right. They might have mentioned the wrong graph because this one has the ethanol and the water that we're looking for. Okay. And if you remember, we are referring to, again, there we go. We want to estimate the vapor pressure. So this is actually the wrong graph here. This is not the right title for the graph. We want the other graph that we're going to get to. Estimate the equilibrium vapor pressure. So we want to know the vapor pressure of water at 80 degrees Celsius and the vapor pressure of ethanol at 60 degrees Celsius. So we're just going to practice reading this graph here. No problem. We can do this. Oops, sorry. I think I'm going the wrong way. Oh. Where did it go? Oh, there it is. There we go. Okay. So all we do is we read this, water. We want this curve right here for water. And we want it at 80 degrees. We go up here, we go to that curve, and we follow it over to the pressure. And it looks like it's going to be, if that's 200, that's 400, that's 300, maybe 325. Okay, if this is a span of 200 here, divide that by 3. So this is going to be, I'm just going to estimate that's around, let's say 325 or so. I may be off. And ethanol, if I remember correctly, it was at 60 degrees. It looks like it's going to be exactly the same, if I'm not mistaken. Okay, let's refer to our answer sheet and see if I'm right or not, even close. All right. Let's see here. All right, 350, 375. Okay, pretty close. 350, 375. And torr is a measurement, a unit for pressure. Okay? All right. That's just practicing reading some graphs. That's all. All right, next question here, ladies and gentlemen. It says, explain how the attractive forces between the particles of a liquid are related to the equilibrium vapor pressure of that liquid. Okay? Attractive forces, so you have one particle and another particle of the same substance, and they're attracted to each other. Okay? This is a liquid. How is that related to the vapor pressure? Well, remember, if you've got a liquid, here's a liquid, and these particles that are in that liquid are really attracted to each other, they're not going to let go of each other very easily. So the stronger the intermolecular, strong, high intermolecular force, that means the vapor pressure, there's going to be less gas up here. There's not going to be much gas that escapes. And not many of these particles are going to escape. You're going to have vapor pressure that is fairly low. It's going to go down. Okay? If this intermolecular force here, if it's very weak, if they really don't hold on to each other very well, then lots of these particles are going to be able to escape from their neighbor and go into the gas. If it's low, then as you can assume, the equilibrium vapor pressure will be higher. You'll have more gas particles up here, and more of them will be able to escape. Now remember, the gas particles increase. As those numbers increase, you're still going to have some that lose energy and come back into the liquid phase. And once you have the rate in one direction equal the rate in the other direction, you have reached that equilibrium, and that's what we're looking at. Okay? Let's just verify. The stronger the attractive forces, the lower the equilibrium vapor pressure. Okay? Wonderful. Okay, let's look at the next one here. Explain the relationship between the atmospheric pressure and the actual boiling point of water. Okay, boiling point is going to be reached when, again, I'll use my example here. There's my container of liquid. All right, the top is open. You have a liquid here, and as that temperature increases, more and more of these particles are going to change into gas. Okay, you're going to have more and more of them reaching the gas. Now you do have air particles over here outside of the container, and those air particles are pushing down. That's atmospheric pressure. So you have air particles pushing down, and you have the gas particles from this liquid that are starting to push up. When these two forces equal, when the atmospheric pressure and the boiling point, or sorry, the vapor pressure are equal, that's when you reach the boiling point, and you have all of these particles now. All these particles has reached the point where they can turn into gas, not just the surface particles. This one can turn into gas, that can turn into gas, that one can turn into gas, that one can, and you start to see that boiling, the bubbling that happens with boiling. Okay? So when the boiling point happens when what? The vapor pressure of the gases above the liquid, the gases that are coming from that liquid, when the vapor pressure equals the atmospheric pressure. Okay? Then you have reached the boiling point. Number 12, explain the relationship between the molar enthalpy of fusion of a solid and the strength of attraction between the solid's particle. Okay, molar enthalpy of fusion, remember this is simply melting. If a solid is going to melt, what has to happen is, remember that solid is in a fixed arrangement. Think of like a cube here. Okay, these particles are arranged in a particular way. They're all bonded together. something like that, you know, it's very, very fixed, okay? Like maybe a cube, crystal. Well, if you want to have this crystal start to melt, and what happens when it melts, it turns into a liquid. Now the particles are free to roll and tumble and flow. Well, that means those intermolecular bonds have to weaken. These bonds between these bonds that keep them in a fixed arrangement have to kind of be broken and weakened. Well, that means if those bonds are really strong intermolecular bonds, interbonds, I'm just put interbonds there. If that's really high, then the molar enthalpy of fusion, you're going to have a lot more energy. Molar enthalpy of fusion, that's going to have to be higher as well. The stronger these bonds are, the more energy, that's what enthalpy is, heat energy, you have to pour into it in order to get those bonds loosened up to turn it into a liquid. Okay? 13. 8 physical properties of water. Water is a fantastic, fantastic liquid. What a gift water is. Okay? There are some really cool properties about water that you should be aware of. Let's just talk about a few of them and check what we have here. All right? Water is transparent, tasteless, odorless. It's nearly colorless liquid. All right, some neat physical properties. The freezing point is 0 at 1 atmosphere. Its molar enthalpy of fusion, remember, is melting. That's how much energy it takes to melt a mole of ice. It expands. This is very unique. This is pretty unique. Water may be one of the few substances that actually expands as it freezes. Right? It expands. The solid is less dense than the liquid. That's why ice floats. Its maximum density is at 4 degrees Celsius, which is not freezing yet. Okay? And as it starts to freeze, it gets less dense, and then the water, the cold water, when it's colder than 3 degrees, starts to go to the surface, freezes, and the lakes and ponds all freeze at the top instead of at the bottom. Okay? Boiling point is 100 degrees Celsius at 1 atmosphere, and the molar enthalpy of vaporization. In order to change 1 mole of liquid water into gas, you need 40.79 kilojoules. Okay? All right, let's do a few calculations here. It says express the molar enthalpy of vaporization for water and the molar enthalpy of fusion of water in joules per gram. Okay, well, all we have to do here, this is for water now. This is for water. I'll do this one, and then you should be able to do the other one. We are given 40.79 kilojoules per mole. I'm going to write it actually like this, 1 mole. Okay? We want to change this to joules per gram. This is just unit conversion. So all we do is, I want to change kilojoules to joules. I want to change kilojoules to joules. Well, maybe you don't know how many kilojoules or how many joules in a kilojoules. But just look at the prefix. Kilo is 1,000. So there are 1,000 joules in 1 kilojoule. Okay? So that will cancel kilojoules when I multiply by 1,000, and now I'm in joules. Then I have to change moles to mass. Well, 1 mole of water, if you look on the periodic table, H2O, an oxygen and 2 hydrogens, that adds up to 18. Just look at the masses on the periodic table, 18 grams. So you will do 40.79 times 1,000 divided by 18 and get your answer there, and that will be joules per gram. And you will do the same thing for that number right there, the molar enthalpy of fusion of water. Okay, I need to see both of those calculations. 15. Calculate the molar enthalpy of vaporization of a substance given that this many moles of a substance absorbs that much energy. Okay, this is vaporizing, and they're basically giving us the answer here because they're saying, what is the molar enthalpy of vaporization? Well, here is the enthalpy, and here's how many moles we have. So for this many moles, it takes that much energy in order to turn it from a liquid to a gas. So molar enthalpy is kilojoules per mole for 1 mole. So if it takes 36.5 kilojoules for 0.433 moles, we just divide them and get your answer in kilojoules per 1 mole. Okay? You'll just divide those numbers. 16. Given that a substance has a molar mass, here's the molar mass, that's going to help us go from mass to moles and moles back to mass, and a 71.8 gram sample of the substance absorbs that much energy when it melts. This is fusion. Calculate the molar enthalpy of fusion. Okay? Well, this time it's just like number 15, but instead of moles and energy, they gave us mass and energy. So we just have to convert this mass to moles using the molar mass. So that's what I'm going to do right here. I'm going to take, right now I have 71.8, let's do it this way, 4.307 kilojoules per 71.8 grams. This is the amount of energy it takes to vaporize this mass of whatever substance we have. So 4.307 kilojoules is needed to vaporize 71.8 grams. But I don't want to keep it in those units. I want to change it to what? Moles. So I have to change grams to moles. And for this substance, we are told we have 259.0 grams per mole. Grams are going to cancel. Okay? And now I have exactly what I want. 4.307 kilojoules times, I have to multiply by, I'm going to divide by 71.8 and multiply by the 259 in order to get my answer in moles. This is going to be moles now, okay? Moles, kilojoules per mole, sorry, kilojoules per mole. Alright, so you just take 4.307 divided by 71.8 times that molar mass is going to give you your answer. Look at the units here. Grams are canceling, so you'll have kilojoules per mole. That's what it has to be in for the molar enthalpy. Okay? Alright, 17 says calculate the number of moles in a liquid sample of substance that has a molar enthalpy fusion of this, given that a sample releases that much energy. Okay, so here's what we're saying. We have 3.811 kilojoules per 1 mole. Alright? That's what the amount of energy that is released when you freeze a mole of that substance. So we take some of the substance, doesn't have to be 1 mole, could be, I don't know how much it is, but we find out that only this amount of energy is released. Or actually, that's a lot. That's way more than 1 mole needs, okay? 83 kilojoules is released. Well, only 3.8 kilojoules is released for 1 mole, and we freeze an amount that releases 83 kilojoules, a lot more. So we must have more than a mole, way more than a mole, right? So we're going to change this to 3.811 kilojoules per mole, but we have what? We want to find out how many moles we have. So we are going to take, actually maybe I should do it this way. Let me set it up this way. I have 83.2 kilojoules, and I know that this substance releases 3.811 kilojoules per mole. This way the kilojoules cancel, and if you take 83.2 divided by 3.811, that'll give you how many moles you have. Okay? Oh, let's see here. Number 18. What volume and mass of steam at 100 degrees Celsius in 1 atmosphere would release the same amount of energy during condensation as 100 cubic centimeters of liquid water would release during freezing? Okay? All right, this one. Let's try to set this one up here. Okay, we're going to have to go back and use probably our molar enthalpies. All right, Okay, this is not an easy problem, but yeah, what we need to do here is we are given a volume of water, and we need to find out what that is in grams and then moles. So we have to use moles, obviously. We're talking about energy here, and our energy is the molar enthalpy. It's molar enthalpy. We got to get to moles. Molar enthalpy of vaporization, molar enthalpy of fusion. All right? So let's do this first. We want to know 100 cubic centimeters. What's the mass and moles of that? Well, here's what we have to do. 100 cubic centimeters. The density of water is 1 gram per milliliter, which a milliliter is the same as a cubic centimeter. So 1 gram per cubic centimeter. So if we have 100 cubic centimeters, 1, okay, that obviously is going to be 100 grams. 100 cubic centimeters of water is 100 grams. So we have 100 grams, okay? Then we have to convert that to moles. And 18 grams for water is a mole. So we have 100 over 18 is the number of moles we have. You can do that calculation. Okay? So if we were to freeze all of that, and we have to refer back to what is the, for water, here it is, here. So for freezing water, you have to take out that many kilojoules per mole. Okay? It's the same amount you put in to melt it. You melt a mole of water, you'd have to put that amount of energy in per mole. If you want to freeze it, you have to take that amount of energy out. And to vaporize it, it's 40.79. Okay? So we would then take this number of moles right here and multiply by the molar enthalpy of freezing or of fusion. Okay, so we'd have to multiply by 6.009 kilojoules per mole. Okay, because remember this was moles here, so now moles are canceled. So let me just go ahead and let's just do the calculation and see if we get it right here. We've got 100 divided by 18 times 6.009. Okay, we get 33.38. Okay, 33.4, and that's kilojoules. All right. Now we're being asked if that amount of energy that is taken out to freeze that 100 cubic centimeters of water, now they're saying, what if that amount of energy is available to you now, and you're going to take it out of water to turn the steam into liquid water. You're going to condense it. So that was what, 40.79, I believe. Here it is, 40.79 kilojoules per mole. Okay? So you don't have 40.79 kilojoules available. You only got 33, so you're not going to be able to condense an entire mole. So you have 33 available, 33.4 kilojoules available, but for condensing, you have to take out 40.79 kilojoules per mole to condense the steam or gas vapor into liquid to condense it. So we take 33.4 divided by 40. Oh, boy. 33.4 divided by 40.79, and we end up getting 0.8. So this is 0.8, 0.81, 0.82. This is how many moles we have. Well, it's asking what is the mass of that, all right? Well, the mass of that, 0.82 moles times mass, 18 grams per mole. So 0.82 times 18, that should give us our answer. Let's just check really quickly here. Yep, about 14. That makes sense. Okay, that 14 right there is the 0.82 times the 18 grams. All right. And then I wouldn't expect you to know this, but to find the volume, so you don't have to worry about the volume right now. We'll actually talk about volume of gases when we get to, there's a whole chapter on gas laws, so we'll worry about that later. Okay, so you don't have to worry about that. But this gives us our 14.7 grams, which is in the answer there. Okay? All right, that was a difficult one, but very doable. Make sure you understand what we mean by the molar enthalpy of vaporization, the molar enthalpy of fusion. Okay? So let me know if you have any questions. Keep working hard, ladies and gentlemen, and as always, I am happy to help, and I'm here if you need me. Okay?